Assalamu alaikum wa rahmatullah. Today our class is to continue the designing of parallel programs. Okay, in the last 2 weeks we have covered all of these topics, actually the automatic versus manual parallelization, and also we covered the understanding of the problem and the program. If we have an existing code, for example, we have to understand the program itself. We have to know what's the hotspots, what's the complicated parts that delays or hinders the performance of the program. And also after that, we have covered the partitioning or the decomposition. And as you know, we have taken two types of decomposition, the functional decomposition and also the what they call it, the domain decomposition or data decomposition. Then we covered the communication. So we learned who is going to communicate with who and how the communication is going to be done and what kind of techniques we need to use. And this communication actually requires the synchronization in many cases. So that's why we learn also what kind of synchronization of programs and what techniques we also can use and so on. Then after that, we had covered the data dependencies. Data dependencies is to show you when the program is depends on the data or when the functions are dependent on the data and so on. And after that, we have covered the load balancing to utilize, efficiently the resources of our machine. Today, inshallah, we are going to cover the granularity, I/O, limits and costs of parallel programming, and finally the performance analysis and tuning. Okay, let us go directly to the granularity. Actually, the granularity I have covered last time in one of our classes, and if you remember, we created a program actually using the granularity, and we made it to flexible to the user to key in how many parts he need to divide the data into and so on. Then after that, based on the input from the user, we create how many threads that we need to handle that data. Sorry guys, I have cough, very strong cough. Yeah. Okay, we came to here. So this is the granularity. Okay, we have some definitions here. So the first thing is the computation and communication ratio. So computation and communication ratio is called granularity actually. In parallel computing, granularity is a qualitative measure of the ratio of computation to communication. Then periods of computation are typically separated from periods of communications by synchronization events. So fine-grain parallelism and coarse-grain parallelism. This is the two types of the granularity that we have, which is fine and coarse. So as you remember, I explained to you using the example of the sand. So in many places, especially here in Malaysia, we have many places. If you go to some islands or in somewhere, you will find some places that have a very coarse sand and some places that has very fine sand, right? So the fine or coarse depends on the size of the sand, right? So here the program exactly something similar to the sand. If let's say you have taken handful of sand and that sand is coarse, then it's similar to the handful of sand is similar to the main program, and the small pieces of sand is similar to the threads, right? So threads could be coarse, could be fine. So the tasks or the functions that given or assigned to thread to calculate or to finish, it could be very big and also could be very small. So if very big, then it will be coarse granularity, and if it's very small, then it will be fine granularity. Okay, let me use the paint here. Okay, okay, guys, this topic is very important, because based on this concept, you will know how to make the parallel programs. So suppose that the program, sorry, suppose that we have this program, okay? So if let's say we divided this program into multiple pieces of code. So maybe this one is the main task, and here at the end we have something to be given to the main task as well. Okay, so these two things we will call them later main thread. Okay, then here thread number 1, and here is thread number 2. Okay, so here this is belongs to main thread, and here also belongs to main thread, and here thread number 1, and here thread number 2. Okay, guys, is that clear?
Clear.
Yes, sir. Thank you, sir.
Okay, so here, as you can see, in total, we will have 3 pieces of the program, right? So the first piece is this, together in one thread. So here there will be some waiting for thread number 1 and thread number 2 to finish in order to allow the main thread to complete the task, right? And also this thread here and this thread here. So now how many pieces we have? It's only 3, right? And those pieces are quite large. So here, if you can understand this, whenever we have less number of pieces, less number of threads in our program, the communication will become very low, right? So the communication needed for these tasks is very limited, right? Because we have only 3 tasks. But if let's say we have 1,000 tasks, then the communication will become very high. Will become very high, right? So we will need to exchange a lot of data among the threads that we have, right? So there's a direct relation between the granularity and the what they call it, opposite relation, reverse relation, sorry. let me draw it here. So this is uh, okay. Okay, if let's say this is the granularity here. Okay, granularity. And here we have communications. Okay, so if the communication, if sorry, let us make this 0 here, and this one it actually is not 0, it's going to 0. Okay, so here this thing actually is, this thing is why? And 0 is somewhere here, because we cannot say the granularity is 0 or the communication is 0. So if granularity and communication is 0, then the program is serial, right? So here, whenever the communication or the granularity increase, the communication will increase, right? Oops, I like that. This one is fine, and this one is coarse, coarse granularity. Okay, so if the program is one piece, that means the granularity is about to be it's 0. So here there is no communication, right? Because it's a serial program and only one piece of code, and there is no other tasks. That's why we don't have to do any kind of communication to finish the task. So if the granularity increases, so we divide the program into two pieces, for example, only, or three pieces. So the granularity is very low, right? Because here we have coarse granularity. Here the communication, if let's say this is the dot here, our program is, for example, uh, something like here. Okay, okay, the granularity is very low, so the number of tasks is very low. That's why the communication is very low, right? But if the granularity increase, for example, let's say we have 100 tasks in our program, so the communication is also going to increase. I flipped the thing, or I don't know what I did. Yeah, I flipped the graph actually. This yeah, this one is coarse here, and this one is fine here. So as you can see, this line, when the communication increase, the granularity become very fine, right? But if the granularity become very coarse, so the number of tasks decrease, then the communication become very low, because we calculate it like that, right? We found the dot like this, right? So the communication is here very low, and the granularity is here very high, right? But what if we take this example here, this dot here? Okay, so here in this case, the communication is the x-axis, right? The communication is very high, but the granularity actually is very fine, right? Because the granularity is here very low, right? So it's very fine. So whenever the communication increase, the granularity become very low, which means very fine. And whenever the granularity increase or become very coarse, then the communication will be reduced until it reach to zero. Okay, is that clear, guys?
Yes, doctor.
Yeah, sorry, I'm a bit sick, that's why my head, I have headache really, and I have cough. Yeah, sorry for that, guys. Okay, uh, okay, one more thing. So in this case, the granularity is what? Who can tell me the granularity in this case? Is it fine or coarse? Guys, what's the granularity here? Is it fine or coarse?
Coarse.
Why?
Only for threads.
3 threads, not 4. What does it mean, 3 threads? It means that every thread have a huge task to finish, right? Have a
Yes.
big task to finish. So this thread is similar to the sand, the piece of sand. Okay. So here, if the piece of sand is big, then it's coarse. If the piece of sand is very small, then it's fine, right? So here, this is coarse. What if we make another example here, and instead of dividing this program into only 3 tasks, then we divide it in like this. Okay, so here, how many threads we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 tasks. Okay, so these 14 tasks are running in different threads, so we have to have 13 threads, but the task of every thread is very small, right? So here the granularity is what?
Fine.
The granularity is fine, right? But we need high level of communication, right? In the previous case, the granularity is coarse, but the level of communication is very low, right? So this is the difference between the granularity, the fine granularity, and the coarse granularity. Okay, what if we have this kind like that? Then we have one thread here and one thread here. What we can say for this? Is it fine or coarse? Guys, what do you think?
Coarse.
Why?
Less number of threads.
less number of threads. But those threads here, 4 threads have very small tasks, but only one have big task, right?
Yes.
Yes. So here, this will become confusing, right? So nobody can tell you this one is fine or coarse, because normally this will be considered as imbalanced granularity. Okay, imbalanced. Why? Because here the tasks are not similar in size. So some tasks are very huge and some tasks are very similar, very small. So the granularity here is imbalanced. Actually, the program is imbalanced. So that's why load balancing of the tasks is very important for the parallel programs to achieve better utilization and to avoid wasting the resources. Because while the first, second, third, and fourth, fourth and fifth threads, they can finish their task quickly. The third thread is going to let them waiting for long, right? So in this case, the resources will be wasted and the performance will not improve and many bad things will happen because of the imbalancing of the load distribution. Okay? Okay, let us continue with this slide. So here, fine grain parallelism, a relatively small amount of computational work are done between communication events. Okay, so here again, small amount of computational work here is done, the red one. Then they have more communication because the number of threads increase, right? So they need the blue lines will become more. So the computation is increased. Sorry, the communication increased, but the computation is also getting smaller and smaller. So this is what they call it fine granularity. So low computation to communication ratio. Here, what does it mean? This means that we do very small size of computation compared to the need of the communication, which means the same thing that I explained. That's why I explained to you in a basic manner. Then I came to the slide here because the slide here sometimes a little bit confusing if you cannot get the idea. But now the idea I think is already with you. So the meaning become very easier to understand. So low computation we done here in the red area. Then after that we go frequently to communicate, right? So we need here more communication. So the ratio here will become small to high, right? Small, computation is small, and the communication is high. So this will give us small number divided by a big number, which will give us a small fraction, right? So that the value here will become very small, which means fine granularity. Then facilitates load balancing. This will help us to do load balancing, even to sometimes based on the nature of the program. Sometimes you cannot do any kind of load balancing because the nature of tasks are to work together. Then each task is different in size by nature, and those tasks by nature are serial. So in that case, you will not be able to do any kind of load balancing. But in many cases, load balancing will become very easy when we can make it very fine grain. Okay, so if we can break the program into small pieces, multiple small pieces, about to be equal in size, so that will be considered as balanced load distribution, and the granularity is fine. So the performance in that case will be very high. Okay? This fine granularity implies high communication overhead. So it improves the computation, but it introduces also high communication overhead, because all of those threads need to communicate with each other. So the communication will create an extra overhead, and there will be a less opportunity for performance enhancement if we increase the granularity. I mean, if we make the granularity fine more than we need. Okay, so breaking the program into very small pieces of code is not always a good thing. So if we increase the granularity to a very high level of fine level, then the increase of communication overhead will also hinder the speed of the program. So we have always to find what level of granularity we have to stick to. So it depends on the nature of the program. Sometimes some programs needs only 3 threads, some programs needs 5, some needs 20. Depends on the application, depends on the problem. So we cannot say that fine granularity must be more than 100, or must be more than 1,000, or must be 5 or 6. We cannot say that. Okay, because in some applications, in some problems, the fine granularity is only 10. The maximum fine granularity is 10. But in some applications, the maximum fine granularity could be 100 or 1,000. Okay? But here always we need to put in mind the balancing between the communication and the computation to avoid the unnecessary overhead, which will hinder the performance enhancement. Okay? If granularity is too fine, it's possible that the overhead required for communication and synchronization between tasks takes longer than the computation. Okay, is that clear, guys? So here, if let's say the computation in serial program, if let's say we take this, we run this task as a serial program, and it spends 30 minutes, 30 minutes. Then we break it into small tasks, for example, 10 tasks, and those 10 tasks could run in parallel. And we tested each task, and we found that each task could take 3 minutes, exactly 3 minutes. So 3 minutes in 10 tasks, it will be 30 minutes in total if we run them sequentially. But if we run each task in parallel, so theoretically it would take 3 minutes, right? About 3 minutes, because the 10 tasks will run at the same time, and each task needs 3 minutes. But sometimes, because the communication is very expensive, sometimes, in this case, we maybe need like 20 or 30 times to communicate between those tasks, or between those threads. Then the communication that we need to have between those threads or those tasks requires about 25, or for example 28 minutes. So here the communication costs 28 minutes, and the execution in parallel costs only 3 minutes or 4 minutes in total. So 3 or 4 plus the 28, it become like 31, while the total time in sequential is only 30. So in this case, the overhead of the communication and synchronization hinders the improvement of the performance. And also sometimes it will improve if we break the program into multiple pieces of tasks, and those tasks have a very high level of communication and synchronization, but the time improvement is very little. So if, let's say, the sequential time is 30 minutes, but after we break the program into 30 pieces of tasks, then we improve only 2 minutes. So 2 minutes over 30 is very little amount, right? So the improvement here is very low. So very low here sometimes is valuable, sometimes is invaluable. So if the program or if the problem is very critical, requires to save every small moment of time, so in that case we will go ahead and continue running multiple tasks to improve the 2 minutes or the 3 minutes or the 2 or 3 seconds. Okay, but if, let's say, the program is not critical and it's not a real time, and 2, 5, 10 minutes are not a matter, and even 1 or 30 minutes are not matter, then in that case we save our time and we just keep the program as sequential as it is before. Okay, you understand what I mean? Guys, is that clear?
Yes, sir.
Yes,
Yes,
doctor.
doctor.
Okay, I will give you one example, guys. One example of real-time application. All of you, I think, knows how the toll works, right? Road toll. So when you come, especially when you have a smart tag in your car, or maybe RFID, so you come normally by your car in a speed of like 50 kilometers per hour or 40 kilometers per hour, and you enter the toll, right? So what you need to do is to slow down your car. So if you slow down your car to like zero speed, then here actually the system, the smart tag and RFID become like similar to the touch and go, right? Very similar to the touch and go, because in touch and go you have to stop totally your car and touch the tag of the touch and go in order to pay the toll and go, right? But that will cause a lot of traffic jam, right? So that's why they come up with the idea of the smart tag and the RFID. So the time here is very important. Time is very important. And also here, each minute we reduce for each car, especially when we have a lot of cars are coming to the toll, each second we reduce for each car, it will become like a huge number of time, a huge amount of time for the people who are coming after like 30 or 50 or 60 cars. So that second, if we accumulate that second for every car, extra second, it will cause after 60 car, it will become 1 minute, right? After 120 cars, it will become 2 minutes. So if we don't save that time, if we don't reduce that time, then the tolls will become always congested, right? So that's why each second we reduce, it's valuable, right? It's money. It's saving time of people, saving petrol for people, because the longer they wait in their cars, the more they waste of their petrol, right? And also the weather will become polluted also because of the exhaust, what they call it, exhaust smokes and everything. So this time in that case is very important. So if, let's say, the program is sequential, then we break it into like 4 or 5 pieces, then we save 2 seconds or 3 seconds. That's very, very good. Yeah, we just go ahead. We don't say in this case, oh, 2 seconds only. No, we keep it sequential. No, because this program is critical. This program is a real time, similar to the fire detection systems. Fire detection systems are real-time systems also, and they are critical. So if the signal was detected late for 5 or 10 seconds, that will make difference. So that's why if we make the program parallel and parallel and parallel to save all the small amounts of time from this task and that task and here and there, so each place we save like half second, 1 second here, 1 second there, and so on, then in total we make our fire detection system more faster compared to the sequential system that would save souls, right? So maybe that will save many people, and also it could save buildings and so on. Okay, so time improvement is depends on the type of the application. Okay, guys, is that clear?
Yes,
Yes,
doctor.
doctor. Yes, doctor.
Okay. Okay. Let us come to the coarse grain. So the coarse grain here, as you can see, the red areas are tasks and the blue areas are communication. So compared to the previous one, here communication is very high, and tasks here is very high and communication is very low. Why the tasks are the communication is very low? Because the granularity is coarse here. Okay, so relatively large amount of computational work are done between communication synchronization events. So here, as you can see, the computation is very high compared to the communication. So if we divide the amount of time we take for the computation and divide it by the amount of time we take for the communication, it will become very huge number, or sometimes become larger than one, while in the previous case, here we have a small amount of time divided by this huge number of time needed for the communication, so which will give us a small fraction and small amount. Okay, so the granularity here will increase while the communication will decrease. Why? Because they have a reverse relation. Okay. So here in this case we have high computation to communication ratio. So the value will become the time of the computation to the time of the communication is very big number. It implies more opportunity for performance increase. This is not true actually. It's not true. It depends on the nature of the program, the nature of the problem. So if let's say this here in this area we have we can break this into independent tasks, totally fully independent tasks. So doing that is going to improve the performance. But keeping it as sequential as that, or as coarse grain as that, that will not improve the performance. It will reduce here, it will reduce the communication cost. But we still have kind of serial program. Okay, because here we have only 2 or 3 pieces of tasks, then that tasks will not improve the time very much. Okay, so here it will improve compared to the sequential in somehow, but that improvement will not be because we make it coarse grain. No. So if we follow this point, that means whenever we make the program coarse, then the performance will increase. But this is not true. Okay? So some programs, when it become coarse grain, improves the performance, depends on their tasks dependency on each other. But some programs, when we make them coarse, the performance become bad. So when we make them fine granularity, the performance increase better and better because they have independent tasks, fully independent tasks. So this statement here is not correct. Okay, I'm going to strike out this. So here, harder to load balance efficiently. Yes, because here we have big amounts of computation distributed over a little number of tasks. That's why we cannot make load balancing. So here, if you can see, the difference between this piece, this area, and that area is very big, okay, compared to the small area here. So the load balancing is very hard, and while here most of them are very close to each other, only this and that are a little bit different. They are still imbalanced, but the balancing here is better than here, okay? So the fine granularity makes the load balancing easier, and the coarse granularity makes the load balancing harder, okay? Then here, which is best? Okay, as I said, guys, we cannot say fine or coarse is the best because it still depends on the nature of the program, the nature of the problem, okay? But if the program has the ability to become fine grain, mostly the performance will be better in fine granularity, mostly, okay? So let us go through the slide here and see the theoretical part. So the most efficient granularity is dependent on the algorithm and the hardware environment in which it runs. So here the hardware and the algorithm itself is very important. So the algorithm here will means the problem itself. So the problem itself and the hardware needed to solve that problem. For example, the problem is relies on sensing some data from sensors, and those sensors are very slow. That thing will hinder the improvement of the program. Okay, so in that case, we cannot actually say that the fine or coarse granularity is better. We cannot say that. It depends on the existing condition of the problem and the hardware needed to solve that issue. Okay? So in most cases, the overhead associated with communication and synchronization is high relative to execution speed, so it's advantageous to have coarse grain. So if this is the case, if the communication and synchronization cost is very high compared to the execution speed, so in that case, better we keep the coarse granularity. But if the cost of communication and synchronization is very low, even if we make it very fine granularity, then we better make it fine granular. Okay, guys? So fine grain parallelism can help reduce overheads due to load imbalance. Okay? Because overheads mostly, if the program is coarse, if the program is based on coarse granularity, then the load will be the opportunity to have imbalance load is very high. Okay, so in that case, there will be a lot of resource wastage. So better to move to fine granularity to improve the performance of that program. Okay, so from here, what we conclude is the granularity actually is dependent on the type or the nature of the program. So in some problems, fine granularity can improve the performance. And in other problems, fine granularity can make it worse and worse because the cost of communication among the tasks is very high. Okay, this is the conclusion. So some problems by nature requires coarse granularity, and some problems by nature requires fine granularity. Okay, this is the conclusion, guys. I hope that you understand. So before I move to the next topic, please, if you have any question, let me know here and now. Okay?
Doctor.
Yes.
So if the speed up is little, right? Is so for example like only 0.3 second, and
Mm-hmm.
then we make it for example like for example the default program is fine granularity, but then if we change to coarse granularity and then the speed up gain is only 0.3 second, it's not worth it, right?
Yeah, depends. Yeah, depends. If let's say that 0.3 second can save lives, then just go ahead. You understand?
Yes, doctor.
Yeah, but if let's say 0.3 second only to, for example, to load a game faster, for example, faster by 0.3 second. It's only a game, right? Nothing critical. So it will be no problem if the player of the game wait for that extra 0.3 second. It's not that big issue, right? So in that case, we save our time, we save our complexity, right? So it
Yes.
depends on the importance of the application, depends on the criticality. So if the 0.3 could save lives, even if 0.1 second could save lives, just go ahead. Just go ahead and take any risk of any complexity and any risk of any extra communication cost or whatever, because the zero point 0.1 second is very important to save lives in this case, right?
Yes.
Okay, clear?
Clear, doctor.
Okay. Now we come here to the input-output devices. So here, actually, this I/O is very important and is one of the inhibitors, actually, of the parallelism. So I/O operations are generally regarded as inhibitors to parallelism. So why they are considered as inhibitors? Because the deal with the hardware, actually in many cases takes a lot of time. So the hardware devices takes a lot of time to respond. So if let's say you send a signal to a sensor to read the temperature, for example, or to read the CO2 gas level or whatever, the response will not be very fast. Why? Because this is going to take little time to do some operations inside the sensor. Then after that, the result will be sent back to you in the program. So this is one of the important inhibitors of the parallelism in general. So parallel I/O systems are immature or not available for all platforms. Okay, so not everything is matured actually in technology related to the I/O. Okay, so for example, I give you one example. All of you know about the HDD and SSD, right?
Yeah.
Yeah.
Yes.
Yeah. Why when we use HDD, our system become very slow, right? Even the startup of the Windows sometimes takes about 2 or 3 minutes.
Because it has a moving part instead of a solid state with just some chips.
Yes, yes, that's correct. But in general, what does this do for us? The moving part takes time to reach the data, right?
Yes.
But that one, because that one is solid state and everything is electrical circuits and so on, that's more faster than the HDD that has the moving parts and that has the readers and everything, right? So that was an example of I/O. Okay, so if let's say the I/O here is the hard disk and the hard disk is HDD and its speed, for example, is 3,400 circle per minute. So in this case, your program anyhow will stay very slow. Even if you make it parallel and you make it fine or whatever, your program still slow because of the hard disk. So in that case, if you improve the hard disk, maybe you change the hard disk, the 3,400 RPM to like 7,200 RPM, here the speed will improve, but still the 7,200 RPM hard disk, normal hard disk is slow. So in that case, if we change it to the SSD, then we will see the improvement even if we did not change anything in the code, right? Same program will improve, depends on the type of the hardware, depends on the speed of the I/O device, right? I think this is very good example for you guys to understand. So sometimes you run a program that relies very highly on the hard disk because it reads and writes a lot of data on the hard disk. Then the program is very slow. You try to make it parallel. Coarse grain doesn't work, still slow. Fine grain is still slow as before. Maybe a little bit improvement, and you say, why this parallel programming doesn't work? The question is that, right? So in this case, I can answer you that the problem here is not a matter of parallelism. The problem here is a matter of I/O system. I/O system is very slow. That makes your program very slow, even though even if you make it very, if you program it in a very high level of parallelism, it's not going to improve because the inhibitor here is the I/O device. Okay. In an environment where all tasks see the same file space, write operations will result in file overwriting. Okay, so if let's say here you have multiple tasks and all tasks are dealing with the same file, so every task reads from the file and save to the file, then all of the tasks are using the same file space. So here, if we did not control the accessibility to that file using look and wait technique, so here the result will become like overwriting of multiple tasks on the same file. So maybe two tasks are overriding each other. So in this case, the result will become wrong and the program performance will not be as intended. Okay, so in that case, this will require to introduce or to use the technique of look and wait, which is going to waste more time for that kind of synchronization. Okay, so read operations will be affected by a file server's ability. If let's say we deal with a problem that needs to read or download files from the file server, FTP server. So the ability of the file server actually is a very important here. So if let's say we have 30 tasks that needs to read files from the server, but the server can handle only 10 files per time. So in this case, 10 tasks will be served and 20 will be in a queue waiting for the server to be ready, right? So this is also considered as I/O, I mean inhibitor, okay? So I/O that must be conducted over the network, so maybe NFS or non-local or whatever, can cause severe bottleneck. So in this case of the file server or the call it NFS or whatever, this is going to be considered as severe bottleneck. Okay, so whenever we write a program, we have to know where are those bottlenecks. Where are those bottlenecks? So the bottlenecks the determination of the bottlenecks in our program is very important to allow us later know about the points of weaknesses in our program to improve them. Okay, is that clear, guys?
Yes.
So this is here the bad news about the I/O. The good news are here. Okay, some parallel file systems are available. For example, GBFS, Luster, BVFS, BVFS2, and so on, and also BANFS, HBSFS. All of those technologies are available to make the access to the file systems faster. And one of those examples is the SSD, right? The SSD compared to the HDD. So that could be considered under this good news, right? So here, GBFS is called General Parallel File System for AIX. This is from IBM. And Luster here is for Linux clusters, cluster file system. BVFS and BVFS2 parallel virtual file system for Linux clusters, which is known as Clemson, Argonne, Ohio State, others, and so on. So here, this technique actually, or this technology is used for Linux clusters, and this is also used for Linux clusters. This one is used for the parallel file system for AIX from IBM only. Okay, then we have PANFS, Banasas Active Scale file system for Linux cluster also. This is from the company called Banasas. And then here we have something called HBSFS from HB. HB storage works scalable file share, Luster-based parallel file system, global file system for Linux product from HP. Okay, the parallel I/O. This is actually general information. Like if you go to even to Wikipedia, you find maybe more information than that. The parallel I/O programming interface specification for MPI has been available since 1996 as a part of MPI-2. Vendor and free implementations are now commonly available. So here there are some open source softwares or platforms that are available and could be used for free to improve the I/O programming interface and performance. Okay. Then here are some options. If you have access to a parallel file system, investigate using it. So if for example, you have a parallel file system, try to understand how to use the features that are available or provided by the hardware that you have. Okay, because sometimes you have a very fast hard drive, but or file system, but you don't know how to use it. Maybe use it in a wrong way that makes they read and write very slow. So if you don't keep reading here, if you don't keep reading, so if you don't know about it, just go and read about it to investigate how to use that parallel file system. So rule number one, reduce overall I/O as much as possible. So better for programs that are especially the real-time programs, we better reduce the deal with the I/O as much as we can. So for example, if let's say we want to save an array, so better don't save it into the hard disk, just put it in the memory, because the memory is faster than the hard disk 100 times. Okay, so that's why your decision when you write your program is very important. Okay, so confine I/O to specific serial portion of the job, and then use parallel communication to distribute data to parallel tasks. For example, task 1 could read an input file and then communicate required data to other tasks. Likewise, task 1 could perform write operation after receiving required data from all other tasks. So for distributed memory systems with shared file space, perform I/O in local non-shared file space. For example, each processor may have temporary file which can be used. This is usually much more efficient than performing I/O over the network to one's home directory. So create unique file names for each task's input-output files. Okay, guys. These 2 points are theoretically more than needed, actually. If I explain about them in practical manner, then the way will be a little bit different. Okay, so if let's say we have some data, for example, let us consider that example of university staff salary. Okay, so in that case, what we need the program what the program need is to read the information about the staff member. So what we need to read is the grade of the staff and the basic salary, allowances, and so on. Then after that, we send them to the trade or to the program to calculate the needed information about the tax and about the allowances and so on. Okay, so in this case, we have to read the information or the data for each staff member, right? So if let's say we make the calculation for the salary is one task for each staff member, in that case, we will have many tasks. For example, let's say we have 600 staff members. So in this case, we will have 600 tasks are trying to access the data from the database or maybe the data from the hard disk. Okay, so in this case, the I/O device will be congested. So this will make a bottleneck. Even though the tasks are fully independent of each other, but they are causing a bottleneck because they deal with the same I/O device. Okay, so in that case, it's better to make one thread, for example, to read the information for the academic staff, maybe, and another thread to read the information about the non-academic staff, for example. And that task will finish reading first, then after that send the data or distribute the data to multiple tasks to complete the computation of the salary. So in this case, we reduce the congestion on the I/O device, right? So that will improve the performance for a very high level of degree. Okay, so here we go to the now we came to the limits and costs of parallel programming. Before we start with this, anyone has a question about the I/O?
No, doctor.
Okay. Let us continue with the limits, costs of parallel programming. Okay, we come here to the Amdahl's law. Amdahl's law, we have already been taking this before in the I think in the third chapter or maybe or the second chapter last time. So Amdahl's law states that potential program speed up is defined by the fraction of code P that can be parallelized. Okay, so this P actually reflects the nature of the problem. So if the problem has a lot of independent tasks, so the B here is very big, so the tendency to have faster improvement or faster performance if we make the problem parallel is very high. The potential is very high. Okay, so in that case, parallelizing the program is going to be highly beneficial. Okay, but if let's say the nature of the program makes this be very low, why? Because the tasks that we have for that problem are independent, like the series that we have taken last time. What they call it? Bonacci. I forget it. You remember that Fibonacci series. So if let's say we are talking about Fibonacci series, so in that case the B is very low. Why? Because the Fibonacci series is has dependent tasks that's why we cannot go forward until we finish. Sorry guys. We cannot go forward. We cannot calculate the second number until we have the first number. We cannot calculate the third number until we have the first and second numbers and so on. So this is considered non-parallelized problem. That's why here the speed up is going to be very bad because the B is very low. Okay. So here speed up is equal to 1 over 1 minus B. 1 over 1 minus B. So if the B is very big, if the B is close to 1, then here we will have small number, and 1 divided by a small number will become a greater number than 1, right? But if let's say the B is closer to 0, so here we will have a big number closer to 1, then 1 over 1 it will become like 1, right? So here if none of the code can be parallelized, so if the nature for the of the program is non-parallelized, so in that case the B will be equal to 0. Okay, B will be equal to 0. So here there will be no speed up. I lost something, right? Yes. And the speed up will be equal to 1, so that means no speed up, no speed up. So if all of the code is parallelized, so the B will become closer to 1 and the speed up is infinity in theory. because this one will become closer to 1. That means 1 minus 1 is going to be 0, right? 1 over 0, it will be infinity. But here the b cannot be equal to 1. It will be very close to 1, so maybe 0.99. So in this case, 1 minus 0.99, it will be 0.01. So 1 over 0, like that, 1 divided by 0.01, it will give us 100, right? So the speed up increased, right? So if 50% of the code can be parallelized, maximum speed up equal to 2, meaning the code will run twice as faster. Okay? Actually, guys, we already explained this. I don't want to waste time repeating the same thing that you already know and you already have taken. Okay? So that's why the speed up, actually they here use different law than the law that we have taken last time. Okay? Because this one is theoretical. This b here is theoretical. We cannot find. We only can estimate. Okay? But if let's say you have the speed up, the execution time of the sequential program and the execution time of the parallel program, then you can correctly calculate the speed up. So maybe this law could be used for the initial stages to estimate whether the program will provide some speed up if we make it parallel or not before we start parallelizing the problem. Okay, but the law that we have taken before is very good to calculate the existing or to calculate the speed up for existing parallelized system. Okay, so introducing the number of processors performing the parallel fraction of work, the relationship can be modeled by speed up equals to 1 over b over n plus s, where p is the parallel fraction, n is the number of processors, and s is the serial fraction. Okay, now things become very complicated, guys. Okay. The good news, guys, for you, this part is not coming to the final exam, so don't need to worry about it too much. We just need to go through it, and at least we have an idea about it. So it soon becomes obvious that there are limits to the scalability of parallelism. Yes, scalability of parallelism is always have limits. Always have limits. So for example, b equals to 50, 90, and 99. So it means 50%, 90%, and 99% of the code is parallelized. Okay? And here are the speed up results. So if let's say the b is 90, so the speed up is 5 times faster or 9 times faster. Here 50 times faster if b is 0.99. Okay. However, certain problems demonstrate increased performance by increasing the problem size. For example, 2D grid calculation, 85 seconds, 85%, then serial fraction is 15 seconds, 15%. Okay, we can increase the problem size by doubling the grid dimensions and having the time step. So this results in 4 times the number of grid points and twice the number of time steps. The timing then look like 2D grid calculations is 680 seconds, which is 97.84, and serial fraction is 15 seconds, which is 2.16. actually they give numbers here, but this is really not clear how they calculate that. Okay, problems that increase the percentage of parallel time with their size are more scalable than problems with a fixed percentage of parallel time. So this is the scalability. If you remember, we have already taken this topic before under the Untitled law. So here, in general, parallel applications are much more complex than corresponding serial application, perhaps an order of magnitude. Perhaps an order of magnitude. So not only do you have multiple instruction streams executing at the same time, but you also have data flowing between them. So the data flow is very important here between the tasks, which is considered as a parallelism inhibitor. So the costs of complexity are measured in programmer time in virtually every aspect of the software development cycle. So we have design, coding, debugging, tuning, maintenance. So here's this complexity actually is a cost. Okay. So parallelism will introduce this complexity, but as I said, if the saving time of the execution could save lives, then we have to take the risk of the extra cost resulted by the complexity to save lives. Okay, adhering to good software development practices is essential when working with parallel applications, especially if somebody besides you will have to work with the software. This is very common actually. So they said you have to use the best practices and so on. Okay, it's a kind of advice. Portability. This is very theoretical information here. Portability here, thanks to standardization in several APIs such as MBI, POSIX, Threads, HBF, and OpenMP, portability issues with parallel programs are not as serious as in years past, however. So portability now, what does it mean? Means we can take our program and run it on multiple machines or run it on multiple technologies like on Linux machine or Windows machine or Unix machine or whatever. So this is the portability. All of the usual portability issues associated with serial programs apply to parallel programs. For example, if you use vendor enhancements to Fortran C or C++, portability will be a problem. Even though standards exists for several APIs, implementations will differ in a number of details, sometimes to the point of requiring code modifications in order to effect portability. Operating systems can play a key role in code portability issues. However, architectures are characteristically highly variable and can affect the portability. So from here we can summarize. So the portability actually has been improved in the last decade due to the availability of multiple platforms or multiple softwares and APIs that helps us to make our programs portable. But in some cases we still struggle, like in this scenario. Also, due to some hardware architecture, sometimes we will have some issues of portability. Okay, if let's say we build the program for a certain or a specially designed machine with the special architecture, then after that we wanted to run the same program on different machine like Windows or Linux machine, maybe 64 or 32 bits or something like that, then it will not work as easy as that. Okay, so we have to take into account a lot of changes that have to be done due to the change of the architecture. Okay, resource requirements. The primary intent of parallel programming is to decrease execution wall clock time. However, in order to accomplish this, more CPU time is required for sure. Then, for example, a parallel code that runs in 1 hour on 8 processors actually uses 8 hours of CPU time. Okay, yeah, because this one, yes, exactly, it runs over for 1 hour on 8 processors, which means about 1 hour for each processor. So if we make it sequentially, it will be 8 hours. Okay. The amount of memory required can be greater for parallel codes than serial codes due to the need to replicate data and for overhead associated with parallel support libraries and subsystems. So here, the memory use in parallel programs is higher than the memory use of serial programs, because in serial programs, normally we don't have communication, we don't have synchronization, and all of that communication and synchronization normally is done through the memory. Okay, that's why in parallel programs, the memory use is higher compared to the sequential. So for short running parallel programs, there can actually be a decrease in performance compared to a similar serial implementation. Yeah, this is for sure. The overhead costs associated with setting up the parallel environment, task creation, communications, task termination can comprise a significant portion of the total execution time for short runs. Okay, so if let's say the program is very short, then we parallelize it, then the extra cost that we will introduce for communication, for synchronization, and for termination of threads and so on, that will cause an extra overhead which will negatively affect the execution time. Okay, the ability of parallel programs performance, now we talk about the scalability, the ability of a parallel program's performance to scale in a result of a number of interrelated factors. Simply adding more machines is rarely the answer. The algorithm may have inherent limits to scalability at some point. Adding more resources causes performance to decrease. Most parallel solutions demonstrate this characteristic at some point. Hardware factors play a significant role in scalability. Example, memory CPU, bus bandwidth on a SMP machine, communication network bandwidth, amount of memory available on any given machine or set of machines, processor clock speed, parallel support libraries, and subsystem software can limit scalability independent of your application. Okay, to summarize this slide, here they want to tell you that scalability is very important, but most of the programs are not scalable in a matter of number of CPUs, for example, because some applications or some algorithms are designed to work only for or on top of 4 processors. So if you increase the number of processors, that extra 4 processors are not going to be used. So here the speed or the program will not have scalability, because it cannot scale itself on different size of resources, on different number of processors. It can only utilize 4 processors. So in this case, the program is not scalable. Okay, but other things like increasing the clock rate of the CPU itself could be or could improve the performance. So in this case, if let's say the program is designed to work on 4 processors, so using processors with a clock speed equal to 1500, definitely will be slower than using the same number of processors with like 3000 megahertz for each processor. So increasing the clock speed is going to make the program more faster, and the scalability here is okay. But for that scenario, if we increase the number of processors, the cost will increase, but the program will not use that extra 4 processors. And also the memory speed, memory CPU bus bandwidth, communication network bandwidth are very important, and most of the programs are scalable in terms of that changes, or in terms of that resource. Okay. So here the last slide, performance and tuning. As with debugging, monitoring, and analyzing, parallel program execution is significantly more of a challenge than for serial program, because here serial program actually is to compute things one after another, so we don't have any challenge. But for the parallel, we have a lot of challenges. So we have to do debugging, monitoring, analyzing to improve and tune the program to provide better performance. So a number of parallel tools for execution monitoring and program analysis are available. You can search online and you can find a lot of tools that could be used to monitor and analyze the programs. So work remains to be done, particularly in the area of scalability. Okay, guys, that's all. So to conclude this slide, whenever you try to build a parallel program, so you have to think carefully, design carefully, debug, monitor, analyze your program, try to tune it to provide better performance, and to reduce the wastage of resources as much as you can. Okay, that's all, guys, and here we finish. Is there any question, guys, before we terminate this session?
No, doctor.
Okay. Okay, thank you for attending my class, and for tomorrow there will be no class. Actually, we already finished. Now we are in the week 11 or 12 now. 12. So we still have 2 weeks. So in the last 2 weeks, I will try my best to give you more practical scenarios, at least to understand and take idea about how to make, or how to create, how to build parallel programs to solve some common issues. Okay. Okay, then I see you inshallah next week. Good luck for you all, inshallah. Assalamu alaikum wa rahmatullah.
Thank you, doctor.
Welcome.
Thank you, Doctor.
Thank you, doctor.
Thank you, Doctor.
Thank you, doctor.
Welcome.